Electricity and magnetism. In 1819, while searching for a relationship between electricity and magnetism, Hans Christian Ørsted set up a current-carrying wire above a magnetized needle. Here's our needle, there's the wire, as seen in this drawing below from a text by Augustin Prévost de Chanel from 1876. And if you're interested, click here to see what a 19th century physics textbook looks like. When there was no current in the wire, the needle aligned with the magnetic field of the Earth and pointed north. So I'm going to say this direction here is north, and the needle is pointing north. When current was supplied, the magnetized needle rotated on the pivot and pointed at a right angle to the electric wire. And this arrow here shows how it's rotating. You know what? Let me erase that so you can see the picture a little better. The direction of this rotation would depend on the direction of the current. Ørsted deduced that an electric current produced a magnetic field that affected the compass needle more strongly than the Earth's magnetic field. So here's a picture of Mr. Ørsted, and he was a physicist and a chemist. In this picture, we have a current-carrying wire, but no current through it. All the compass needles are pointing north. Then a current was put through the wire, and look at this. All of them are pointing in a circle around the wire. By wrapping multiple turns of wire, forming a coil, about an iron core, there's our core in the gray, an electromagnet is created. When current is applied, the electromagnet acts just like a permanent magnet. The iron core increases the magnetic field created by the current in the coil. When the current is removed, the electromagnet loses its magnetic properties. The strength of an electromagnet is increased by, well, 1, increase the current coming in, and 2, increasing the number of coils of wire about the core. Further research and development led to the creation of stronger electromagnets. This is an industrial electric magnet that picks up large metallic objects when the current is turned on. Metal scrap, so all this stuff down here, is being attracted from the ground to the electromagnet. An electric motor is created by winding multiple coils of wire about an iron core that can rotate. So here's our multiple coils circling our rod here, our iron core. The core is then placed within a magnetic field created by a permanent magnet, which is represented by blue on one side, pink on the other. When current is supplied to the coils, the magnetic field exerts a force on those coils and the core rotates. Electric motors convert electrical energy into mechanical energy. Shown here is one of the first electric motors that was ever built. See all the coils here? And that would rotate this thing. Once physicists find one phenomenon, they try to see if the opposite also works. So what would they look for now? This was their question. Could a magnetic field create an electric current? And the answer is yes. Michael Faraday, who's this gentleman over here, discovered that a changing magnetic field will generate an electric current. This phenomenon is called electromagnetic induction. An electric generator uses the same internal parts as a motor. It is just run in the opposite direction. This time the coil is spun by an outside force. Right here you're having some outside force rotate the core, and that would produce electricity coming off the wires here. It's just the opposite of a motor. Faraday's discovery of electromagnetic induction played an important role in the development of the electric generator. An electric generator transforms mechanical energy into electrical energy by rotating a coil of wire in a magnetic field. Shown here is a simple generator in which the coil of wire is rotated through a magnetic field by turning a handle. So here's the handle. You just rotate that rotates the coil, and since it's within a magnetic field, it will light up this little light bulb. It's producing electricity. The coil of wire in a commercial electric generation plant is turned by harnessing the force of falling water or steam. The coil of wire in the electric generator in a car, called an alternator, is turned by rubber belts driven by the engine that are connected to the pulley shown on the right over here. So mechanical energy is converted to electrical energy in an electric generator. So here's our generator, this turbine electric generator. We've got a kinetic energy source, which can be steam, combustion gases, flowing water, wind, whatever. As long as it can spin this rotor, it spins this piece here, which is called the stator, that generates electricity. It's sent out over power lines all the way to people's homes and businesses and workplaces and manufacturing, whoever needs electricity. The relationship between electricity and magnetism enabled James Clerk Maxwell to unite these two forces and fields into the electromagnetic force and electromagnetic field.